stop me in between. My name is Nikhil again, and thank you, JB, for way too kind of an introduction. Let's see. So today, we're going to have two parts. In the first part, I'll basically give you an overview of terminology and the details of what basically means to do machine learning. And then we'll do a simple example by basically coding a regression model by hand from scratch in scikit-learn. And the second part will go more towards model selection and how do we measure performance of different models. And it will be like a primer for the tomorrow's much more advanced lecture on model selection and cross-validation. So hopefully this will give you enough background to dive into more detailed stuff tomorrow. And we'll end the second part by doing actual autism data fMRI classification problem. That brings me to the next question. How many of you actually downloaded the GitHub? Oh, cool, more than I expected. Okay, so if you haven't, please do that because it might take a while if everybody's doing it at the same time.
And again, don't hesitate to ask for help.
Right. Both Nadia and Per should know the GitHub repo, and so if you're having issues downloading things, then just ask them about that. Cool. All right. Before we start, since you're still COVID and masking, let me ask you. Yeah.
Apparently, the audio is level. Can you just all stop your microphone just in case that's the problem?
Maybe we can ask whoever's on now.
Also, my laptop has a terrible mic, so if somebody else has a better laptop with better mic, can just keep it here, and I'll talk on that as well. It's the same laptop. Is that better? It's better? Can people hear on Crowdcast? No? Okay. Okay. Cool. So, yeah, so this was kind of like an example of, because we are still kind of, I guess, pretending there's COVID or not pretending, I don't know. But the question here is, okay, we have population of 1% of COVID prevalence. And then I train a simple machine learning model based on some of your biometric data to basically diagnose COVID patients. My laptop, the model shows I'm 91% accurate. And you also calculate 90% sensitivity. So for people who haven't done machine learning before, it's basically the probability that the prediction is positive if patient has COVID. And 91% specificity, that means that the prediction is negative if patient doesn't have COVID. So now the question is, what are my chances that I have COVID if my test is positive? I mean, we all probably have been through this experience in the last 2 years. Who wants to guess? Okay, how many people think it's A? 9 out of 9 in 10.
1, 2, 3, 4, 5, 6, 7, 8.
The other question you will have to think about if you work for drug companies or, I guess, population science. Okay, how many think it's 1 out of 2? Oh, wow, no one. You're sitting one. You can't. Okay, you have to pick one choice. Okay, you can't pick all the choices. So half. Okay, who thinks it's C? 1 in 10. Oh, there's 1 in Crowdcast. 1 in 10.
Okay.
And 1 in 100. Anybody? 1 in 100.
2, 3.
Oh, 2 of them.
No. Okay. 1.
Okay. All right. So next, okay, keep this on hold. Next question. Now, since we all want to be fancy AI researchers, we decided to train an AI model, maybe a deep net, UNet, VNet, whatever, or ResNet, whatever you want to call it. But for this, we use CT scans and then brain MRIs because COVID does affect brain. And this model has 99% accurate, and with 80% sensitivity and 99% specificity. Now, who thinks we should use deep learning model versus who thinks we should use simple model? Okay, who thinks it should be the first simple model? 1, 2, 3, 4, 5, 7, Who thinks it's the other one? So I guess everybody else is, or people are, okay, you have to pick at least one. Okay, all right, cool. Well, sadly, I'm not going to tell you the answer, at least right now. So let's see if your answers change by the end of the talk. But that brings me to my first point, where basically, like, training a machine learning model, you have some input and you have output. It's actually the easiest thing. You have scikit-learn, you have NeuroAI, you have PyTorch, you have TensorFlow. So you have data, you can always train a model with like a few lines of code, and you will get some results. The harder part is how do you pick the features from your input data, which model to choose, because you can have multiple models or thousands of models, and what is the good performance metrics for the task that you're doing. And a good machine learning engineer or scientist basically thinks about these things more than the actual nitty-gritty of the model training, especially if you're doing applied science, right? So if you're all doing neuroscience or biology or life sciences, you are more interested into these peripheral parts of machine learning rather than the actual the calculus or the linear algebra of machine learning. Cool. So all of this kind of fits into what we call a validation paradigm. So every choice you make needs to be validated by some objective metric. And so the question in terms of machine learning for us usually is, how do I validate all the choices that I make for my features, for my model selection, my performance? And that's where the whole cross-validation and other types of validation paradigms come into play. Cool. So just so we are all on the same page, there's a lot of buzz of machine learning and AI and all that stuff. So just to define, that's like almost like a Wikipedia definition. It's a study of computer algorithms that improve or learn mapping between input and output automatically using a lot of data. And it's a subset of artificial intelligence, machine learning itself. And then the neural networks and the AI or the deep learning is an even smaller subset. I don't know if you guys can see this of the whole machine learning realm. So since most of you are probably from biology and neuroscience backgrounds, so we use it in neuroscience. It's because, I mean, especially, so I personally deal with brain, so most of my examples will be about brain. It's incredibly complicated. So understanding the relationship between different brain variables and behavioral stuff or cognitive stuff, it's extremely complicated and non-linear, and so it generates a lot of variables. So if you're looking at voxel level data, there are millions of voxels for individual brain. If you go for synapses, there are more than a billion. If you go for genetic stuff, there's also millions of different SNPs you can get. So all of this generates a lot of data, and mentally it's very difficult to comprehend. So machine learning can really help you find useful relationships if you do it correctly. So that's kind of like the rationale why we try to use machine learning, or why we get excited about machine learning in neuroscience or biology. But it's very, we have to be very careful in choosing what type of problem you want to solve, especially when contrasting with the classical statistics, basically GLMs and type of things. They have very different reason or different rationale or goals for that type of statistical analysis. Whereas in machine learning, usually you want to do machine learning if you're interested in some sort of prediction task, or if you're interested in low-dimensional representation, and both of them kind of map onto supervised versus unsupervised learning algorithms. And I think you must have heard this over last year many, many times, or at least I have said it many, many times. To do machine learning, you need a lot of data. So you need a lot of examples to find meaningful relationships between your input and output. Okay. So this kind of summarizes what we just talked about in a bit. So yeah, usually in machine learning, you have number of samples or examples, as people call it sometimes. They're usually represented by different rows. And the columns represent different features. So these features can be, in neuroimaging, we usually have brain images. In genetics, you could have SNPs or some sort of other cell assays that people use. So that basically generates this large input matrix of number of samples and number of features. And then your outcome is basically the labels, which is usually a single column of one label per example that you have. And your goal is to find a model that will map this relationship between the input X and the output Y as accurate as possible. So far, so good? Am I going too fast, too slow? Everything is okay. Mentally, at least, and also I think scikit-learn does a similar thing in their nice classification of different machine learning algorithms. It basically can divide them into supervised and unsupervised, and we're going to focus on the supervised learning today. But even within supervised, you can also think of them in terms of what's your outcome. So your label can be a continuous variable. Say if you're predicting a disease severity, so it's a clinical score or age or something like that. Or you can basically classify it categorically, and that becomes a classification problem. So you'll see both of these models today, regression and classification, and we'll focus on the supervised learning part today for the time we have. That's more than enough, I think. Okay. So in a simplest way, what machine learning is basically learning a bunch of weights. So if you have a model, model basically is represented by a different set of weights. And the goal of machine learning is to learn these weights, also sometimes known as parameters of the model, that give you the most accurate mapping between input and output by using the number of examples you have. Now, these weights are come in different flavors in a way, and that basically gives you different classes of models. So linear regression is basically you're trying to fit something within those points as the surface says in 3 dimensions, or if it's 2 dimensions, it's going to be a line. Support vector machines is trying to separate, we have something called hyperplane, so it's trying to separate 2 groups or 2 classes away. There are also more popular tree methods or random forest. Also, there are all tree ensemble methods, which are all decision trees, and many times so it becomes a forest. And more recently, you have this more complicated artificial neural networks, which are more of a hierarchical models that can embed nonlinear relationships between input and output really well. And so depending on which architecture you pick, you get a different set of weights, and you get a different way of learning those weights depending on your learning process. And we'll talk about that in a second. But every model has its own like pros and cons. So depending on what type of data you have, you will kind of have some prior knowledge what type of models you want to pick. But on top of that, you still need to compare models through validation, cross-validation paradigms. So you can compare the performances of models on your specific data. Cool. So just mathematically speaking, I know there are a few equations there, but I hope that they are not too complicated. And it's always visually looking at linear regression, it's more intuitive when we're talking about what is learning or what is model fitting. So linear regression, as probably most of you know, it's basically a linear combination of your input variables. So if you see basically x1 and x2 are the input variables, and they basically have these beta coefficients. So the beta coefficients are the model weights or parameters, and the y is your output. So what we really want is find these beta coefficients which give you the most accurate output as possible. And so the accuracy here is measured by the mean square error. So the difference between your prediction versus the actual value. And so smaller this difference for all the examples you have together or on average, the better your model is. Does that make sense so far? And to do this, the process is called gradient descent. And we don't have to go in details for that, but visually what it looks like is basically you start with this random set of weights, then you calculate the loss or the mean square error for those weights. And based on those that loss, you change your weights so that the next time you calculate the loss, it's going to be smaller. And at some point, it's going to saturate or it's going to basically plateau. And then you get the weights, which are basically the optimal weights you can find for this data. So this is what's happening here. In the beginning, we can pick a random weight, that is this line, which is basically the model that we are choosing to fit this data, has a really bad I mean, it's way away from the points itself. But as this process continues, we update the weights, and then the line gets closer and closer to the points or the data we have, and it basically slowly stops at some point where the weights of that line, or basically the beta 0 and beta 1 of this line, is the optimal weight for this data, and that's essentially what model fitting is. Does that make sense? Yeah.
Just for people to know, like that's the general principle. For actual linear regression, there is an algebraic direct solution, so you don't actually have to do that iteration, let's say. But that's better presented in a way, because that's really the general principle for many of those algorithms and.
So just to be clear, in this model, there are only two parameters. That's beta 0 and beta 1. And this is because visually you can only see 2D on the plane. You technically could have hundreds of variables and they'll have hundreds of model weights, but you won't be able to visualize this on a 2D surface. But the process stays the same. You calculate the weights, you calculate the mean square error, and you update the weights so that your mean square error next time will be smaller than before. Very good? Yeah. Cool. I think that's what we talked before. If people who are more computationally interested, this is what like the landscape for the optimization function looks like. And what happens is, so these are basically where the mean square error is the smallest. But in more complicated models, like JB said, this is one I showed is the most simple one, especially if you have more nonlinear models like random forest, neural networks. Here, you only had like one way to go to the bottom. But in more complicated models, there will be many minima or local minimums. So you not always will find the best solution for the model. So especially if you're training more complicated models, like neural networks, for example, there is no guarantee you will find the best solution all the time. So there are other heuristic methods you can try, which basically give you better chances of finding the best solution, but there is no guarantees usually. So just keep that in mind. The solution you find for a complicated model may not be the optimal solution all the time. Cool. Okay. So far, we have basically given a free hand to this gradient descent. Like, okay, this is my data, find some solution for me. But in practice, that's not always a good idea, because sometimes we have some prior knowledge about our data that we want to include in the type of model we want to learn. So for example, some of the diseases we know there are only a handful of features that should predict this disease, or some handful of genes that should predict this disease. So even if we're collecting data for 10,000 genes or 10,000 voxels, we know the information lies only in, say, 100 voxels. So there are ways to basically enforce the learning process to learn only 100 features, or 100 features that are more predictive than the others. And this is where basically something called regularization comes into play. And what regularization does is basically, while you're learning these parameters from beta 0 to whatever beta 10,000, beta 1 million, it will basically decide, okay, do I only want a handful of my parameters or coefficients to be positive? I want them to be small. I want them to be with specific characteristics, and all of that can be added to your learning process. So the model you learn is more plausible in your like a commonsensical way. That's one of the reasons. The other reason being, especially in neuroscience, we usually have way more features than the examples we have. So for neuroimaging, we have, say, 1 million voxels, but only 100 subjects. So there is a practical risk of overfitting your model. So that basically, I will talk about the overfitting again later, but it basically means you'll find some solution that will only work for your data, but not for anything else. So all of these problems can be mitigated if you do something called regularization. But in a sense, what it means is like I'm going to embed some of my beliefs about my model in my training process. So the model I get back it's more realistic than whatever random, whatever the model learns by itself. It's more like, okay, when you're teaching kids or teaching, you don't let them do whatever they want. We have some constraints in our educational systems or at home with parents. So it's like you're basically putting some guards for them, so the model itself does not go off the rails. So it basically gives a kind of a framework within which the model can learn certain things that we want it to learn. And again, you don't have to go to the details of the equations per se, but you must have heard these words, so I wanted to go over those at least once. There are two most commonly used regularizers, which are called lasso and ridge regression. So lasso, also called L1 penalty, which what basically does is forces only handful of weights to be positive or non-zero, and most of the other weights will be zero. So at the end of the day, if you go back here, even if you have say 10,000 features, like some majority of them will have zero coefficients next to them. So when you're doing prediction, only the features which have non-zero weights or coefficients next to them will be used in your model prediction. So that's what lasso does. It will basically force a lot of weights to be zero during learning. So only a handful of weights will give you the predictions you want. And whereas the ridge regression or ridge regularization forces weights to be small. So if you have large weights, it's very likely that your outcome will fluctuate very fast. So it's always not desirable. So it's usually desirable to have small weights, the value of the weights to be small. So that's what ridge does. So both of these are basically techniques or tactics to get models which are more stable in practice and more realistic in terms of the true relationship between your input and output. Does that make sense so far? And computationally speaking, what it does is basically, like I said before, the way we train is by calculating mean square error. So before, the mean square error was just the difference between your predictions and your actual values or your labels. For regularization, what we do is basically add another term on top of that as part of your mean square error. So what it does is basically modifies how you calculate mean square error, and that gives you a different set of weights that will optimize that mean square error. I mean, this is just like people who are interested in technical part of it, but I hope you get the idea behind lasso and ridge. If there are questions, no? Cool. Yes.
Are the slides already online?
Yeah. There should be on the GitHub as well. So GitHub thing has something called docs, and docs will have the PDF version of this. Cool. So now we're going to start an exercise, but just to give you an example before that. Okay. Most of us will use scikit-learn these days. People also use R or MATLAB, but this is mostly scikit-learn focus. So we'll talk about scikit-learn. So all of this I've told you so far, you never have to do it by hand. Scikit-learn will do all of this for you. And I'm just showing some of the commands here to walk you through. And then we'll do actual example from the GitHub repo that I sent you guys out before. So the first step would be just import some libraries from scikit-learn. So we are going to do a linear models, a linear regression model to be specific. So we import those models from scikit-learn. There's some fake data that I'm putting here. So it's just like 2 examples and 2 features. And then you have basically 2 labels for each of the features. Then the next step is to basically decide which model to use. Here I'm using linear regression. We can also use SVM, but let's stick with linear regression for this example. And all I'm saying is take a linear regression, and this alpha is basically my the lasso parameter. So the one here I was talking about before. So we're going to use the lasso regularizer, and this is where I'm adding this additional term for my mean square error calculation. And the alpha basically decides how strong I should penalize my model. Basically, how many weights I need them to be 0. The sparsity of the model is decided by this alpha. So if I want my model to be very sparse, so very few features to be active during my prediction, then I have a very high value of alpha, and vice versa. And the next step would be just to use our data and tell the model to do fit. This whole gradient descent process is all automatically done by scikit-learn for you. And it will give you a model that now has model parameters that give you the prediction. And then finally, you can take a new sample or any sample and use a function called .predict, and then you will get a prediction for this model on a new data. Is the process okay? Cool. I'm not sure. Okay. This is going to be very small for you guys to see.
Those projected on broadcast as well.
Yeah. Actually, let me. Okay. I'll go a bit further and hope that this gets a bit darker in the next 15 minutes. And then we'll go to the actual example. Okay. So first step is, okay, we have trained a model. How do we measure the performance of this trained model? So say if you have 100 samples, I train more. Do I use all 100 samples to train my model? And that's usually very bad thing to do. So what people do is we'll split it into train and test subsets. So you'll train a model on a train subset and get basically these model parameters from scikit-learn that we just saw, and then apply that model to a new test subset which model has never seen before. And the performance on that test subset is what we usually report. Because if the model has learned things well, then it should generalize to any other test set that it hasn't seen before. Otherwise, the model is just memorizing some relationship in your train set, and it's not really actual learning, but just memorizing things. So yeah, so first question, and this will be a recurring theme in this presentation, the question you should be always asking during machine learning is your model generalizable? And what that means, will its performance generalize to a new unseen data set after you've trained it? Okay. Let's see. So in practice, what usually happens is your train performance and test performance will never be equal, or it's similar. And so there are two types of things that happen when you're training the model. Either your model is too simple and it does not capture the relationship between your input and output, and that's called underfitting, or your model is too complicated and instead of just learning the relationship, it starts memorizing things between your input and output in your training set. And both of those things are bad. So it basically, as a machine learning designer or engineer or scientist, it's your job to figure out how do we decide on the complexity of the model so that both of these things don't happen drastically. So to give an example, again, we're going to the whole, so your input here is basically this x variable, which is basically slightly curved. But if I pick a simple linear model to describe this relationship, it's going to be underfitting to this shape of data. So the optimal stuff here is basically the one in the middle, where it's slightly curved, maybe a second order polynomial. And if I pick a much complicated model to fit this, I could technically go through every single point. So in my training, I would be able to predict every single input and output relationship perfectly. But as soon as I go to my test set, both my underfitted model and overfitted model will do really bad. So the performance will not generalize to a test set. So on the left side, you can see the model is underfitting. So it basically has very high bias, whereas on the right side, it's overfitting and it's varying a lot. So it has a very high variance. So that's kind of what people mean when they talk about bias variance trade-off. And that translates into your design choice of picking way simpler or way more complicated model. Is that clear here? Any questions? Yes.
I'm not sure I understand the graph of the top right.
Oh, top right, yes. It's a bit small to see here. So the x-axis is model complexity. So when I say that, that's how simple your model is, how complicated your model is. And it's a rule of thumb, more number of parameters you have in your model, more complicated the model is. So simple and elegant models are the ones which have very few parameters. But if you get too simple, then it won't be able to capture the relationship between your input and output, which is what's happening in the left bottom here. So as on your left side of this axis, you are basically have a very high bias because you're forcing the model to be as stringent as possible. And most of your error comes from your bias of the model. So say if you're predicting a disease, but if I choose my model to only focus on variables that have nothing to do with disease, so it will never predict disease. So I'll have a very high bias towards predicting controls because my model is not sensitive to the features that actually describe the disease. So that's what my error will come from my bias of my model. Whereas if I increase my complexity, which becomes like this basically, then in my training set, I have a perfect mapping from my input to output. But as soon as I go my test set, that sort of noise fluctuations in my training set will not be replicated in my test set because literally when this up and down is coming from noise, it's not actually trained of the data. So on the right side of this model complexity, your bias goes down, but your variance goes higher because slight change in your input, your model will fluctuate a lot, and that's really bad when you're trying to predict on your test set.
You select the variance curve versus variance explain.
Sorry?
The variance, like the blue variance curve, represents the variance explain.
It's not really variance explain, it's the variance of your model weights. So how is easy? So if I just remove one or two examples in my training set, will my weights of my model change? And if your model is good enough, it shouldn't change that much based on just a couple of examples. If it's really capturing the trend. But if it's very sensitive to your input examples, then slight change in your input example will give you a drastically different model. And that model is not stable.
Maybe the extreme example of that is, let's say you take linear regression and you have as many data, as many parameters. Your predicted data will be exactly your data, with zero error. Right? As soon as you change and you try to predict on new data, that's going to fail. So that's the extreme example of a fitting. You have perfect fitting on the training data and very likely extremely poor fitting on the test.
Cool. So this was an example for like a regression type of thing. So you can have a similar ideas for classification or categorical variables, basically. So you're trying to separate two classes, say controls and disease. But the actual boundary between those two classes is curved. But if your boundary itself is just a straight line, you're underfitting because you're not actually capturing the true nature of your decision boundary between two classes. Or if you go too zigzaggy, I guess that's the technical word, then you'll separate the classes perfectly in your training, but not in your test set. Which is why it's very important that your model works well on your test set and not just training set. So far, so good? Cool. So I think I'll stop here and we'll go to the first example. Does anybody have issues downloading or installing, or does everybody have? You can probably not see this. How do I? Does anybody know how to change the dark mode versus light mode for VS Code? Because maybe light would be easier.
file, under file, it's preferences. On the
I
top
can't even
one,
see file here. Okay, file.
preferences.
Yeah.
And then color scheme.
Cool. Yeah. Is that better? Yeah, perfect. Where do I go? Okay. So the first thing to do is the regression tutorial. And don't worry, I will walk through every single line. The reason to do this, despite the popularity of notebooks, is notebooks are great. I will use them for my next tutorial as well. But at the same time, I think it gives you a lot of confidence if you can code in proper Python script, because when you actually do the analysis later and publish your work, this will be much more easy to use for other people and share results, and just you'll make less mistakes, because notebook can be tricky for certain things. So if you have VS Code, you can use it directly in VS Code. If you prefer to just use like your own other IDE or some text editor, that's completely fine. What we're gonna do is go line by line. So there is a tutorial and there is a solution. So you can just run go through the tutorial first, and if you get stuck, you can of course look at the solutions if you really get stuck. But try to solve them on your own, because making mistakes is a really good way of learning things. So what we'll do here is first, okay, the idea basically is to train a model on a diabetes data. And scikit-learn is really good at giving you this dummy data sets, or actually well characterized data sets. So we're going to just use the data set from scikit-learn itself. The first step is, I'm basically giving you the scaffolding of the entire tutorial. So the first step would be just to load the data set. And so if you run just this code by itself, can you guys see here? Maybe I should. Well, let's hope it runs from here. So if you have environment set up, this should just run as well. And example, this is where the code is for me in this path. So I go here, and my environment is called Ring Compute. So that's what I'm loading for my Honda environment. So you can do the same. And once you're there, you can look at the files, and literally you can just run Python ML regression tutorial. And it will do, it should run some stuff for you and basically give you it's too big for the screen, but there we go. So it should print something like this. So all of these basically give you different stages of this tutorial.
But
And
can you show again how you get from on VS Code, because I think most people are on VS Code. Can you just link like activate the environment?
Right. So the VS Code is usually either on top bottom or sometimes in the top upper top right corner. And you click there and you basically pick the environment that you have in this list.
So there's the list environment, is it?
It's in the, so it's hard to see in the screen because it's getting cropped, but
okay, on the bottom right for some.
Yeah.
So you have to look at where the environment is. Yeah.
Okay, that's fine. Okay, yes.
So how would you pick a normal feature number?
So this was given to us by our data set, right? So if your data collection or whatever your assay is gives you a certain number of variables, that's what you start with. And then you have to make a call on do you want to even further reduce the dimensionality using PCA or ICA type of things, or you want to just select features based on some lasso type of thing that you're doing. So it's a design choice here to do. For this example, we are not touching that yet. We are just basically trying to see what does it mean to learn the model. Okay, does anybody else have the mean square error for the random weights? Anybody? Okay, just to clarify, if you're not familiar with Python or scikit-learn, the way to multiply things in Python is it's a function called dot. What dot does is basically takes two vectors of numbers. So for us, it's the number of parameters, because we want to multiply each parameter with each feature for each example. And this function basically encapsulates that into one-liner code. So this line of code basically does what we were doing by hand in the slides, like this whole regression equation or linear regression equation. This is what this dot function is doing in one line of code. So if you're confused about that, that's what it's doing. Okay. Question? You're good? Do you have the mean square error? If you need, you need some help right now? Okay. Okay, who has finished until here? Okay, somewhat. Okay. Yeah, I will move forward a bit, and there'll be a break after this. So if you got stuck before, we can talk about that and solve their issues. The second step is now we want to train the model, right? So far what we did is basically take a random set of weights, use our data to do some random predictions, and as most of you found out, it gives you very high mean square error. It's basically saying your model doesn't understand the relationship, because literally that's random weights. So the next step is to use the linear regression. So you're going to pick the model linear regression and use the data we have from only from the train set. It's very important. We use the train set, not the entire data set. And use the train set to fit the model, and then use that model fit to get the predictions later on, and then find a mean square error for our training set. So I have actually done this for you for your training set. I just want to make sure you guys understand the process. And I think what you want to do is
There's a question here.
yes.
That's the to-do says you have to find the y-hat, but the line just below.
Yeah.
The line just below seems to show the solution already.
Yeah, I think I copied the solution. I was trying this out myself. So you already have the solution, but I would like to know the numbers that you guys get. Yeah, so do you? What I want to know is, do you have the new train mean square error? And is it smaller than before? Yeah, it's like a tenth of what it was. Okay.
The tenth, that's what it goes. Something over there.
Yeah? Yes?
It seems to be smaller, but not that much.
Not by much. What's your error?
2850.
And how much did you get?
Oh, so now I'm getting 2850.25
For the.
for the train.
How much was it before?
And before it was 28,000.
So that's the order of magnitude smaller,
Yes,
right?
yeah, 1/10.
By 10. Yeah. I think that's correct if I remember. We'll see the solutions in a minute as well. Okay. Is this, so if you're writing a paper and you get this result, is this what you write in your paper?
I don't think.
Why not?
It's training and we haven't used it.
Exactly. So now the next step would be to do what?
So apply it on the
Exactly. Is everybody clear on this thing? Yeah, I think I already given them solutions.
Maybe after the
Yeah, like almost done. 5 minutes.
Just keep the solution, this one, and then put like
Anybody has test results?
Yes, the same. It's very similar.
It's very similar. Okay. Anybody else? Yeah. Cool.
Is it simpler or bigger? Or smaller?
Uh,
Bigger by a little bit, yeah. So in principle, could it be smaller or not?
But yeah,
Why? I mean, like, I'm just asking.
It's just
Like, you
different.
think,
it's just different data. I'm guessing it could just be a.
by chance, it
Yeah,
could
by
be
chance.
smaller. So the question is how that will be smaller, or how to work consistently across data.
Okay. For sake of time, I'm going to walk you through what was supposed to happen until now. So what we first did is we tried a random model, right? These have so all these weights you see here 0.5, 0.07, 0.97. These are completely random. They have nothing to do with the data, and that gave us mean square error of about like 28,000 or in that range. Everybody might get different, but that's the range. What I wanted you to see after that is once you do training, the weights you get are completely different. So now the weights you see are like positive and negative, high and low type of thing. So all of these weights are very different. And that will give you a different mean square error, which is 2850. So beware, but these are like everybody will get slightly different weights because there's some stochastic elements in this. What would I have to do if I wanted these weights to be very small? So if you see the weights are like -8, 248, 511. Who knows what would I do if I want to keep these weights small values? Sorry?
I think maybe using regularization.
Yes, which one? Yeah. So range prediction will force these weights to be smaller. Of course, your mean square error might be different, or actually will be different. But sometimes it makes, if you're trying to interpret the weights or have some meaning, it can make sense sometimes to have certain types of weights. Okay, so that's the error for trained data. And as most people pointed out, this is not something is what you would report. What you would want to report is the test set. And so what we do is take the trained model and apply it to the test set. And if you see, the results are comparable, but not exactly the same.
So what do you mean when you say the weights would be sparse?
So if the weights were sparse, most of them will be zero here. So if I had the L1 penalty on top of that, so I would have most of these weights would be zero. And the stronger the penalty I have, more weights will be zero. So you're forcing model to be simpler. But now it's arbitrary, not arbitrary, but it's like a designer's choice how simple model you want to do. But if you go too simple, then it will underfit. Yeah.
And obviously, we learn how to actually tune those parameters. If you have enough data, you can tune how simple should be the model.
Okay. Who can tell me what would have happened to my error, like the test error, if I was overfitting to my train set? So you want to say it louder for everybody
It
else?
would be very large, like very large.
Exactly. So it's one of the good diagnostic technique. If your train set performance is great, but your test set really sucks, you're most likely overfitting your train set. So that's a good way to know if your model is way too complicated or you have very less data. So if you don't have enough data, you will overfit. When I say less data, I mean less examples. So that's very careful because you may have huge number of features but very few samples. That's when you're likely to overfit, and that is usually reflected into your test performance because your model is not generalizable to your test set. Yes.
The part of the code where you initialize the coefficient, that part is not. It wouldn't be necessary in practice, right? You're just showing us basically that you can initialize them. Because that was
Exactly. Yeah. That was just to show what happens if you have random weights. The scikit-learn's model.fit will take care of all the initialization and the training for you. Okay, and the last part I wanted to show was the figure. Can you guys see the figure? Such a tricky. Okay, hope that's better. Okay, so what this figure shows, on the thing that's cropped here, but the bottom should say the true outcomes. That's your true Y labels, and your Y-axis is the prediction. Okay, the perfect model is the one shown in blue. Will basically give you exactly identical, like your predictions and your true performance will be exactly same. So that's a perfect model, right? The one we have is the orange one, which is basically the predictions and the true values don't align in one line. So you have this kind of a spread around your predictions. Okay. So what I'm trying to say is basically your performance of your linear model or your model usually is going to be between the best model, which is going to be zero error, and the dummy model. So dummy model here is no matter what, I'm just predicting just one value. So no matter what my true value is, I'm always predicting 150 as my, and this 150 comes from it's a mean of my my labels. So it's basically coming from, if your model is really stupid and can only do one thing, it will predict the average of all the predictions you want to predict. So that's what the dummy model is. So when you're trying to train models, it's very good to know what's the best and what's the worst possible performance you can have. And the way to do this is through these dummy models. And if your model performance is better than a dummy model, you're learning something. And I'll stop here because I think everybody's tired. But if you have questions, we can just still talk during the break. But it's going to be 10 minutes break. So it's 10:40, so 10:50. But like I said, I will go fast at the end. So if you have questions, I'll be here and we can talk.
Thank you so much for the presentation. It was very interesting. What if we have just a few parameters, like a few features? What would we expect to see, for example, in terms of test number? We would expect to see again a large error,
So
it's a bias.
It's a trade-off between number of features and number of examples. So if you have a lot of examples and very few features, then you're unlikely to overfit. So because you have a lot of examples, so basically your model will find the trains correctly, but it's possible to underfit because your features are not predictive of the task you're trying to do.
Exactly.
So it's more likely to underfit than overfit.
Yes.
But for underfitting, you basically, so this is kind of what I guess. So you have this error, right? Usually in practice, you have expectation of my error should be smaller than this.
Okay.
But no matter what you try with your data, then your error will never be smaller than that. So it's underfitting, which are not capturing the true. So if you have very few features, a lot of data,
I mean, in ideal scenario, you will do just fine because you have a lot of data to find a relationship. But if your features are not representative of the information, then you will underframe and then you won't get expected performance. Then get more performance as good as the expected performance.
Okay. Yeah. Okay. Yeah.
Yeah, but the caveat there is sometimes it also depends on which model you use. So just because this model could not find a relationship does not mean that other models will. So then you try a few different models, and then you do them. I'll talk about the models later, and then you basically have to figure out which model to pick from the available data. But
It's a bit.
Are there any questions, concerns, comments? No? Cool. All right, so if you get confused with the Python stuff or whatever, the messiness of the screen or whatever, there are solutions in the thing. So you can always run the solutions and try to understand what's going on. One thing I wanted, like we talked about this, is like you don't care about the train performance, or really, it's not the one that you decide your model based on. So you decide on the test set, right? So we talked about this. You're going to do this. You have 100 samples. You get 90 as train and 10 as test. But which 90 and which 10, right? So that's a choice that I have to make. And every time you have to make a choice, you can always be wrong or just lucky. So that's where the idea of doing the same process again and again, or cross-validating in a loop comes into play. So instead of just randomly picking one 90%, one 10%, we're going to do this again and again. So we are not just lucky or unlucky for the split we get for the first time. Okay. So how do we do this? So this is called cross-validation, and the first part of it is the outer loop. And the goal of outer loop is to figure out how do we sample our train and test set. Okay. So if I have 100 samples, like I said, I could pick in multiple ways. I could pick my test set. So what cross-validation does is gives you a way to basically create these splits many times. And the most common or most popular one is called k-fold, which means I'm going to do this process k times. And every single time, I'm going to basically pick a different test set. So if I have 5 folds, I'll pick 20 samples which are not overlapping at all every single time. And I'll keep the remaining 80 samples as my train set. Is that clear? Yes?
It's clear, but I just have a question. How do you know how many to do? Because you often like read articles and like, oh, we chose 10. But like, they never explain why. They just say that's what they did.
Most of them pick 10 because previous people picked 10. So I mean, as you do more and more machine learning, you realize this at some point it becomes arbitrary. But for number of folds, it really depends on how many samples you have. So if you have thousands of samples, you can do more folds. If you have few samples, you won't be able to do more folds. That's one, I guess, unhelpful answer. But one thing you should be careful, there's one trade-off though, right? So say if you have 100 samples, and if you decided to do 10 folds, so you have 90 in train, 10 in test. So every time you're picking 90 samples for your training set, they're not changing much. So in a way, your models are very similar to each other. Whereas if you pick smaller training sets, if you only pick 50 as train and 50 as test, so you only have 2 folds now, you may not have enough data to train the model perfectly or good. So it's a trade-off between, do I pick larger training sets, that means more folds, but similar training models, so the models become more and more biased, or do I pick smaller smaller training set, but I may not be able to train the models well enough. And this really depends on how complicated your data is, how many samples you have, and there is no good theoretical way of estimating this easily. So that's why people just pick 10. So it's easy. You can just point to the papers that they do. One thing you should never do is leave one out. You should never have just one sample in your test set and all the remaining samples in your train set. If that's the case, you can be almost sure you don't have enough data to do machine learning. Because say if you have 100 samples and using 99 of them to do a train set, there are essentially very similar samples every single time. And since you only have one example, you can't even get variance of your test performance, right? And you only get one number. But that gets in the nitty-gritties of cross-validation. And tomorrow, I think Jerome's going to talk more about those things as well. The idea here for me to give you, why are we doing this type of thing? Hopefully, the logistics of it become more clear tomorrow. But they get messy very easily.
This is another error maybe quite often, especially in the samples data sets we're working with. They're not very good, right? If you go into classic machine learning things, they laugh about it. Which is fair enough, I guess. But one thing you probably are subjected to is imbalance, class imbalance, right? Like we have one class or later one way more samples than what the other. If you're not careful and tell your cross-validation to adjust for that, you will end up with biased performance from one or the other. Because if you have, I don't know.
Yes, that gets pretty complicated, but I guess the gist of that point is when you're splitting train and test, you want to maintain, say you have 2 classes like healthy and disease. If they are not 50-50 in your 100 sample, if you have 80 and 20, that proportion of 80-20 of disease versus healthy controls should be reflected into your train and test sets. So it's in scikit-learn, it's called stratification. And again, you don't have to do this by hand to count number of sub-disease, and you can just tell scikit-learn to do it for you. But the point being, every time you do these splits of train and test, you try to keep the distribution of your labels as close as possible in your train and test set. But anyways, so the key point for outer loop is I don't want to make arbitrary decision on which train and test set to pick. So I will do this again and again, so I'll get this cross-validation. So the question I'm answering here is basically, how do we sample train and test sets? So far, so good? Okay. Now, I was briefly talking about, we may not just have one model. We can have multiple models. You can have linear regression, SVMs. Even in linear regression, we can talk about regularization. So we can have a linear regression with lasso, with L2, ridge, or whatever type of things. So we don't really have a way to figure out which is the best model if you just have one train and one test set. So the next part of this it's called, again, cross-validation with inner loop. One thing I want to emphasize again and again, these are all the choices that you're making
as a machine learning scientist or engineer, we never want to make these choices while looking at our test set, because in real life, we don't have access to the test set. So when you're doing this analysis in the lab, we pretend that there's a test set that is not, we don't have access to it yet. And so all the decisions you're going to make about model selection should not depend on the test set where we will measure our performance on. Because if you do that, it's called double dipping. It will become a bit clearer in a second. So the point of inner loop basically is to make these decisions of your model selection, if you have multiple choices, without looking at the test set. So to do that, what happens is, okay, now I have 100 samples again. I pick my first 80 to be my train sample, other 20 to be test sample, and I don't touch this at all. And from my 80 samples, I do another cross-validation loop by splitting that 80 samples into 4 folds, for example. So there are 20, 20, 20, 20. And out of those 4 folds, I pick one as my validation set, and remaining 60 samples as my train set. Okay, I'll explain a bit again. So the point here is to evaluate different sets of models and see which model works better for our data. But to do that, we shouldn't be looking or peeking into our test data, because in reality, in future, we don't have access to that data. So if we do use that data during our models training or model selection, we are double dipping. We are basically looking at future without knowing it, or we shouldn't be knowing it. So the inner loop basically tries to build this firewall between the test set, which is supposed to be inaccessible to us, and do this another inside inner loop where we train our models now on this train set, which is basically now 60 samples, not all 80, just 60 from the train set, and evaluate the model performance on this validation set. So if I have 4 models, I will basically get 4 test performance sets or 4 performances on this validation set. Okay? And it's the same logic. Why did I pick this split, right? So I don't want to make this arbitrary choice, so I do this again and again. And this inner loop, basically I get my model performances for, say I have 5 models, I get 5 models. So I get 5 performances. And I can basically then select what is my best model in my inner fold. And then I just pick that model, and then I evaluate the performance on the test set. Does that make sense? I know it's a bit, well, literally convoluted, but yeah. So again, the idea is not to select model based on your test set, and also not to select a model based on one arbitrary choice of your training data. So you split your training data multiple times. You basically measure the performance of all possible models or regularizations or hyperparameters that you have on your inner loop, and then pick one model and then use that on test set. Yes?
So are outer and inner loop used together, like differently, or do you pick either the inner loop or outer loop?
So in scikit-learn, it's just one command. So you just tell the model, do 10 outer folds and 5 inner folds.
The outer loop does use all the data, right? So it'd be creating models based on that testing data that we don't want to use in the inner loop? Or am I missing something?
Right, so this is where it gets bit, well, so this is just one instance of it, you're right. So when I'm selecting model for this inner loop fold, I'm just still part of my first fold of my outer loop.
Okay.
Right. So in this first fold of my outer loop, I'm doing this entire, that's why it's called nested cross-validation. We are nesting cross-validations within cross-validations. But the idea for the inner part of the inner nested cross-validation is to pick the model. So that's a model selection loop, right? And the part of the outer one is to make this check, basically want to get a distribution of our performance of one selected model on multiple splits of train and test. So they're completely different goals in terms of what you're trying to do. The key point here is like, we have to make some choices here in terms of train and test splits, or we have to make choices between which model to pick. And we never want to make that choice based on just one performance. So that's why we do the outer loop. We split train and test multiple times, so we get distribution of our performance. And same for inner loop. We split our train set multiple times, so we get distribution of our performance for our different models. Again, this will be explained in more detail tomorrow in a more of a mechanical way of doing these things. But again, the idea here is just to show why are we doing this, so you won't be lost tomorrow when it gets more technical. Does that make? Is it clear? Like, why are we doing this? I see a lot of confused places, but still agreeing.
Maybe do it. Just say it once again. Just make sure that.
Okay, so we have 100 samples. Okay, you all agree we can use all of the samples for training. We have to split train and test. So we split 80 and 20, right? So the first 80 samples are my train sets, and 20 are my test set. If I just had one model, I could just do the outer loop of my cross-validation. Like right here, I just pick different 80 and 20 every single time. So I get 5, basically if I have 5 folds, I get basically 5 test sets, which means I get 5 performances for a single model, right? So now I can report the performance of my model. I have this average performance of my model. And life is easy. But like I said, there is no, we may want to try multiple models, right? We cannot try multiple models in this framework and just report all 5 performances on my test set. Because in theory, we don't have access to the test set. So to basically select the model without looking at the test set, we have to do another cross-validation pretending we don't have a test set. Okay, so now we have this train data, which gets split into another cross-validation loop. Now think of this is as like just another cross-validation loop, and we basically again held out some of the data as our validation data. And then we basically train all our models, because we have multiple models, on this train set, and check the validation performance of those models. Yes?
And then after you did that, you would, if you did another split of your test train, you would do this again.
Exactly, yeah. So it's like it's a nested thing. It's like Russian dolls type of thing. But again, here, every time I do this split of train and validation or train and test, I don't want to do it once, which is why we do it multiple times. That's why this becomes like a shifted validation set. But again, the goal of the inner loop is to figure out which model works better for my data without looking at the test set. Yes?
Then if you repeat doing train and test for the next second time,
yeah,
you would expect maybe to see another model pops up.
Right. So in the next round of this train and test outer split, yes, you are now. It's basically it's a next iteration of the same process. So that split will also have train and test set, but again, that train data will not have access to the test data in that split. So we are still picking a model which is optimized for that iteration. Yeah, they will. So yeah, so every fold you have for the outer loop, like basically here, they will all yield different models, which means different parameters. So if you have linear regression models that we saw before, they had like 10 values for the coefficients. They will have all different coefficient values. The goal of this process is not to find. Well, we are not really that concerned about exact values of the weights. What we're concerned about, can we have a process by which we can predict well? So we're interested into the distribution of our performance of our models that we're picking. Individual weight itself is not that critical in this process. Does that make sense? What the end of this process, what we can basically say, I have this fancy neural network or this particular SVM class of models, or maybe linear regression with lasso works much better than the linear regression with L2. So we are basically making statements like this where we know what type of model works really good on this data. Yes, sir.
Just clarify that at the end of the inner loop, you have only one model with
yes.
one set of coefficients.
Yes.
And then you test that model in the outer loop.
Yes.
Just to get the distribution. So at the end of the other loop, you don't select just the mod, the wait, the same one. Okay, yeah.
Right. So for each, after the end of each inner loop, you only get one model.
Yeah.
Okay. But what he was saying is like, since you're also in outer loop, you'll still get 10 different models if you're 10 folds.
So the outer loop is just to get the distribution of your accuracy.
Exactly. You're getting a distribution of your performance for the class of models you're trying to find.
Yeah.
Yes.
What is the total number of iteration in this specific case?
I think that goes back to her question there, like how do we select number of folds? It's a trade-off between more folds you select, your models will be more similar to each other because your training set stays almost the same. But if you select fewer folds, that means your train set is small. Like say if you have 2 folds, you have 50% in train, 50% in test. That may not be enough data to do prediction. So it's a trade-off between how big your data set is, and it's not a trivial thing to answer. But like what I told her before as well, just don't leave one out cross-validation. That's the extreme case of this, and that's usually a very bad practice. But people usually kind of for outer fold, people go between 5 to 10 folds. If you have millions of samples, you don't even need to do all of that. But if you have around thousands of samples or 100,000 samples, you do 5 to 10 folds for outer fold. And I think scikit-learn by default does 3 folds for inner loop. So for not this one. For the model selection part,
The number of folds defined separately for outer and for the
yes, yeah. Because it will exponentially increase, well, not exponentially, polynomially increase the compute time for these things. Yeah. This is really important because bad cross-validation will give you bad results, which get published all the time. So if you're unclear about this is the time to ask. But we will go in details more tomorrow, but it will be more technical rather than conceptual. So, cool. Right, I think I briefly talked about hyperparameters in a sense, but basically hyperparameters are design choices basically. So these are not learned by the training process. What? It's died again.
Yeah.
Okay.
Sorry.
So hyperparameters are never learned usually, and they're chosen. So hyperparameters are like, okay, what should the sparsity of my model for Lasso, for example? That's something I pick. Or do I pick supervector machine with a linear kernel or radial basis function kernel? With neural networks, it's even complicated because there are like literally thousands of design choices you have to make due to how many layers. Any questions on deep learning?
So, for example, that is an example of hierarchical models.
Yes.
So, for example, imagine that you put a number, and first thing that the different parameters could be color, and the second shape, and the second how many lines are like until you get to the correct identification.
So that's kind of true for images. It's not the same thing for the language or other things. So more complicated the shapes you have, more layers you would need intuitively, but there is no hard and fast limits. Also, it's not clearly, okay, the contrast parameters are in the first layer, the color in the second layer, the shapes in the, it doesn't work like that. We hope it works like that because it's kind of based on the visual cortex organization of human brain. There is some truth to that. Okay, some of the models that are trained in a very specific way will show that sort of segregation of low-level features and high-level features. But like I said, there are millions of parameters here. So getting that really nicely layered thing, it's not always possible. But intuitively, you would go from simple to more abstract features over time, over the layers. Yes.
And maybe Elizabeth Dupre's talk is going to give you some information on that specific aspect.
Yes.
There's a question online, and could you explain the first quiz question? Why is it 1 in 10?
I tried, but I can go again.
Just briefly.
Right. So 1 in 10. So the line above that, what is it? It's basically gives in a sample, like a use case. So if you have 1,000 individuals, can they hear me? Okay, there are 1,000 individuals. That means the prevalence, if it's 1%, that means there are 10 COVID patients in those 1,000 sample. So remaining 990 are healthy. So that's the split we have for COVID versus healthy. Now let's focus on the COVID patients. So we have 10, and the sensitivity of my test is 90%. So out of those 10 patients, my test can definitely detect 9 out of 10. So that makes it, I have 9 patients, which will be true positives. And similarly, if I want to know how many of them are false positives, I have to look at my controls, which are 990. And given my specificity is 91%, that number turns out to be 89. So total positive patients I have from this test is basically 9 plus 89, which is 98, right? So out of those 98 patients which get marked as positive by my test, only 9 of them are true positive. So 9 over 98 is almost 1 in 10. So it's not exactly 1 in 10 if that was the issue of the, I was just trying to be concise. But it's close enough to 110 than anything else. Yes?
Could it be said that part of the idea of this is that if you train a model, even if it has great performance, you should always consider the population that you're studying, or like the type of distribution that you have in your.
Of course. I mean,
idea, I guess.
Yeah, the prevalence kind of comes from the label distributions you have. If you only 1% of COVID patients in your entire data set you have, you kind of know the prevalence. So you should definitely take that into account. So that's one thing for sure. Also, like as we talked about this, what is more important to you? Is it true positive, true negative? For classification, for regression, it becomes a different question again. But think critically, what is important for your model to predict? So that is more important than do I get perfect accuracy, because perfect accuracy may not have any meaning for your problem. This makes sense? Cool. This is, I think, the last slide I have. Well, no, just a couple more slides. This is, I'm trying to summarize the mistakes I have made, not in my life, just in machine learning. But basically, few things you want to take away from here is the cross-validation stuff, right? So cross-validation stuff, what it avoids is double dipping. What double dipping means, I think I briefly mentioned, is like if you have any knowledge from your test set during your training or model selection, then that basically is cheating, essentially. So your performance of your model that you're reporting is biased, usually inflated. It's usually worse. It's really much better than it should be. You should also be considering about, this is getting very common these days, especially in neuroscience. Most of the data sets we have are from North American demographics or European demographics. So models you're training will work really great for them. And that's also true for AI, actually. AI has a lot of biases, like you can see, basically racial biases in the US. There have been a lot of news about that. And so it is very important to be cognizant of the fact that your model, your training is essentially can only learn the things from the data you have at hand. It is not a general purpose thing that will work for all the data sets. So you have to be very explicit about the limitations of your model when you're training those. The next couple of parts are more specific to neuroscience or biology or life science stuff. It is very common in this field that people don't agree on labels. So by what that I mean is, okay, if you're classifying cats and dogs, everybody agrees what's a cat, what's a dog. For diseases, it's not the case. Not everybody agrees what is autism. Not everybody agrees what is Parkinson's. So if your ground truth itself has some noise in it, it's much challenging to train a model where you don't trust your ground truth itself. So those are additional challenges that come into play. And the data distribution shifts, again, it's a very difficult but a very important topic. If again, I'm going back to neuroscience again because that's where I work. We constantly get new scanner upgrades, you get new protocols. There are different vendors who provide you the scanners. I'm assuming it's the same for the life sciences. We're doing all these assays for proteins or genes, slight changes in your basically tools, hardware, software will affect the distribution of your data or the quality of data. And it has to be, so that's why you need to basically be aware of this and try to get as much heterogeneous data you can to get your model more stable. If you're only training on one specific niche data set, it's more likely than not, it will only work on that data set. So it's very important to collect different types of data, not in terms of just the samples, but the intermediate processing that happens on your raw data as well. So this is a whole whole realm of reproducibility and replication studies. And sadly, AI, especially in neuroscience, has a terrible track record of like replicating anything that works. So if all these thousands of papers gets published, very few can actually replicate on something else 6 months later. Yeah, I mean, this is also like this was, I think, more relevant a few years ago. Everybody was doing deep learning. It's like, no matter what data I have, I want to do deep learning. More often than not, in neuroscience or life sciences, you don't have enough data, or there is no need for doing deep learning. Like I said, deep learning is good for your structured data. If you have just a handful of features, you're much likely to do good with random forest or some tree ensemble methods than in deep learning. Okay. Oh yeah, I had this as well. Cool. I wish I had this when I was starting up, so I put this here. It seems very trivial and silly in a way, but it helps a lot. So if you are trying to start a new machine learning analysis or study, first you should know what is my number of features and number of samples. I mean, you might say it's as simple as just doing dot shape or dot length or something, but more often than not, there are missing values. So if you are missing values, how do we handle missing values? Do we drop the features or do we drop the samples? It's not as trivial as it seems. So it's very important to first decide what number of features and what number of samples I want to have, especially if you are missing values, because especially in medical field, there's a lot of data with missing values. Then the second thing, I guess that's rather simple. If you have categorical data, it's like you don't want model to think it's actually continuous data. Say if you're doing diseases and 0, 1, and 2, the machine will think 2 is bigger than 1, so this is more severe than the other. That may not be the case all the time. So there is encoding methods like one hot encoding type of thing, which binarizes everything. So you have to be careful in terms of how you encode your data itself. And I didn't want to talk too much because scikit-learn has a really good example on how to do that. So there's a link on the slide there. This is kind of comes up all the time. So I especially want to talk about this one more time, the double dipping part. So what happens is we talked about we don't want to use information from test set, but sometimes we do this unknowingly. For example, it's a common practice to take a z-score from your data to basically normalize your input distribution. But if you take the z-score on the entire data set before splitting it into train and test, you're using information from your test set. Or if you're doing PCA, on the entire data set, then you're using information from your test set. So it's always important to split the data first and then do any operation that you're doing. So always imagine test set as something you don't have access to. So if you don't have access to, you cannot use that for any of the operations. Cool. I think we talked about this anyways in the questions. Like, again, just to say, we should be very aware of the performance metrics because performance metrics are not the same as your machine learning training metrics or the loss metrics. So they're different. So be aware which metric you really care about. Yeah, and I always know what it's going to be our lower bound for your performance. So what's the worst performance you can have, which is called a dummy or null models usually. So if you're doing classification, for example, we talked about if the model is just predicting everybody to be healthy, your null performance technically is 99% accuracy. But you don't want that. So your sensitivity is very bad there, which is 0. So your null performance for sensitivity is 0. So you want to know what is the null performance of your model, so you can be confident when you get a model that it's doing better than the stupidest performance you can have. So we didn't talk about regression too much for that, but it's going to be a median value. So if you're predicting the severity of a disease, the null model will just always predict the median of that disease, the range of the symptom values you have, or the severity values you have. So your performance will be based on model that predicts just the median value. So if you have a trained model, that should do better than that. It is important to know null performance is not the same as random performance. This is not random. So null performance is very specifically doing the same thing. So you're either predicting the same class all the time or predicting the same value all the time. It's not predicting a random value. It's a very specific value it's predicting. And lastly, be careful interpreting the parameters or the weights of the model. Like I said, machine learning goal is to do good predictions. It's not primarily interested into understanding what the parameters mean. So fight the urge to assign meaning to the model parameters. It's very tricky and more often than not wrong when people do it. So unless there's a very specific reason you want to do it, don't try to interpret machine learning model parameters right off the bat. Cool. I think we have till 12. Okay. So I want to go to the next example. But like this is more like something just like food for thought type of thing other than anything else. But if you want to take one thing away from this presentation is you have to do multitude of validations. So your goal is generalizability, and that can only be confident if you do many validations. So cross validation is just one of the standard ways of doing it. But if you really want to be confident, you also need to do it on multiple data sets. So you can do one cross validation on one data set, then you get the model, then you try multiple data sets. So it's not just one-time thing. It's a more iterative process. And like I said, the training part is easy. Validation is much harder. So you should focus most of your time trying to validate the model so it's generalizable across data sets. And no matter what you do, there will be a bias. There will be an error in your model, and it's important to try to quantify that. And lastly, it's mostly like more advanced topics in machine learning or AI these days. Can we have model explain what it's doing? Because that's also very important for clinicians to explain why this person has certain disease rather than just blindly trust. So there are all these interesting topics, especially in life sciences, that are coming in for AI. So if you're interested into that, you can definitely check those out. And I think that's the last slide I have. Are there any questions before we go to the last example? Questions? Yeah.
So I was thinking about that, so for example, if you like a super complex deep learning model, so you can only get a prediction, you don't know what's happening, right? But is there a way, is it valid, for example, remove a feature and then set the accuracy and then include that feature to see how much accuracy it has? It's not a roundabout way to get individual feature prediction value.
In theory, yes, you can assign it. You can assign some sort of importance to that feature by just removing it from one thing. But there are two issues with that. First of all, if you have millions of features, you can have to do it a million times, which is very complicated, intensive. On top of that, sometimes individual feature itself is not that important, but the combination of features, right? So if you're recognizing a face, it's a combination of your facial features, different points. So removing just one of them may not change anything. So it's the combinatorial aspect of these features is very computationally intensive to calculate and also assign meaning to. So most of the deep learning models, especially, if you had one feature that did really good job, you don't need this model to begin with. The reason you need complicated model because there's a complication relationship between some set of features that you have. So trying out one by one does not tell you anything about how they will do well in groups.
For example, like let's say you have like 2 scans, so you have like 2 sets of like 1 million thoughts or 1 million features. Can you do like, is it okay? Is it more okay to do like 1 scan and the other scan and the conversion? Just like, you know what I mean? Like not like individual features, but like sets of features with like share that feature.
Yeah, I mean, so you can definitely compare modalities, for example. So you can do a cross-validation on one modality with the other, and you can say, it tells you that, okay, this modality has a higher, the way you frame this would be like, say, this modality will give me higher prediction performance. It still does not tell you anything about the biology, at specific regional level. It tells you, okay, this modality is better at capturing the information I need to make my predictions. But if you're interested into if like a hippocampus is predictive of cognitive decline in schizophrenia, machine learning is not the way to go. So it's the questions about biology / descriptive or explanation of what's going on. It's different than the questions of, can I just get an answer that is useful to me? So segmentation problem, you don't care what the weights mean. As long as I get a good segmentation of my scan, I'm happy. So the problems like this are really good for machine learning because it doesn't matter how I get there. But if there are questions are related, how do the underlying etiology or underlying process that is explaining some biological phenomena, that becomes more of a question of moral interpretability. And even forget about deep learning, even linear models, if you start applying regularization, interpreting of weights becomes very complicated. So if you have regularized model and you're trying to interpret the weights in a biological way, that can go wrong in many, many ways. So it is about, it's not, because it's about the goals or the goals of objectives of these models is different than, let's say, classical statistical models where you're trying to basically do t-tests or ANOVAs to understand, assign meaning to all these variables. So it's a very different goal. So even though mathematical process might be similar, the actual goal is very different. Yeah. Cool. Who has energy to do another example? Cool. All right, so I hope this is visible. Okay. If you guys are tired, let's just be honest. Are you guys tired? If you're tired, we can just go through the solutions. You can do the tutorials on your own time. But this is an example where we're trying to basically classify autism individuals. Because so autism is a very good example where the labels are noisy, so it gets tricky to do. So the 2 tasks we're going to do here is like use the functional MRI data to classify autism versus non-autism. That's one thing. And the second part we're going to do is basically the data set comes from different scanners or different actual sites or different labs. So we're going to try to predict, if I have a scan, can I tell which site it comes from? And we're going to basically see what is easier. Is it easier to predict autism or is it easier to predict which site it comes from? Okay. All right. So if you have already downloaded the data, I think I'll just run through solutions. So because I think we only have 10 minutes and I see very tired faces. So I will go through solutions. But again,
But your tiredness.
Huh?
But you.
It's fine. What we'll do is try to, but if you don't understand any of the cells in the code, just like raise your hand and we'll try to go through that. Okay, the first step you're going to do is basically, again, we are using libraries here, which are, NileLearn. So are you guys familiar with NileLearn? So I think there's a tutorial on NileLearn as well. So NileLearn is basically a machine learning library for neuroimaging data sets. So it simplifies machine learning and other encoding and decoding analysis on imaging data And it has a very similar syntax as scikit-learn. So it's basically a machine learning adaptation for neuroimaging. And it also comes with its own data set. So we're going to use the data set that they already have, so you don't have to worry about the whole data set itself. So what is this doing is going to download 100 samples or 100 examples. And each of the subject basically has functional scan. But, and each, let's see if it's probably, yeah. And it also comes with like a diagnosis file. So there's a CSV, or that basically tells you, if you run this, like some different subject IDs here, and the site ID, and basically diagnosis. So there's a 1, I think if it's autism, 0 if it's not autism. And then there's also, I don't know if you can see it here, but there's also a column for site ID. Yeah, so there's site ID as well. So if you want to, for the second part, we're going to try to predict which site it comes from or the location, and that gives you here. So this CSV basically serves us as like creating our output or labels for this data. And the download we just had, or hopefully you guys had using this command, will give you the input for your data. But as any neuroimaging, okay, so let's if you run this, you should probably see. Can you guys see here at all? At least on your screens, hopefully you can see. There are 100 samples. And what does subject feature shape mean here? So what this means is this is fMRI data. So are you guys familiar with functional MRI? It's basically a brain scan with time component to it. So for each subject, you basically collect a time series of a bold signal, which is on different regions. So there are 196 time points and 111 regions. So this data basically contains, for each subject, 196 time points and 111 regions. So that's a matrix you will get. So far, so good. And if you want to plot this, it looks like this. So this is a parcellation on the brain. So it basically color codes different regions from where we are basically collecting the data from, or averaging the data. And it's just like one slice of the brain. So you'll see you'll have a lot of slices. So far, so good? Okay. But yeah, so this is just a spatial of the regions of those. Now from each of these regions, there will be a time series, right? So that time series is hard to visualize on the brain. So what we do is visualize in a matrix. So that's what it looks like. So this is again for one subject. Like I said, there are 196 time points when we have sampled the data, and we had 111 ROI. So for each ROI, you get this time series. That's what it shows here. I hope it looks prettier on your screen than this screen. But going back, like imagine the first slide I showed you guys, right? There's a matrix of features and subjects, and there's output. So what we want for each subject is just one vector. So we need to basically reshape this data into like a one vector per subject. And the way we do that is basically find correlations. Well, one way we do that. It's not the only way. One way we do that. So what this metric represents is like a correlation between the time series between each pair of the ROIs. So for example, this point right here is basically what's the correlation between ROI 49 and 55, something like that. So the diagonal is always 1 because it's correlation with itself. So far, so good. So the shape of this matrix is going to be what? 111 times 111. So that's because those are the number of ROIs we have. Okay. But like you said, you can probably see it's a symmetric matrix, right? So the top and bottom triangles are identical. So we literally just want one of those triangles as our input because it's a duplication of information. So that's what we are trying to do, basically. So we take the indices from the lower. You could also take the from upper, doesn't matter. And when we do this, we basically get a vector of 6, 3, 26. So what I have done basically take the input data, neuroimaging data from an individual and process it and flatten it into a one vector of these many features. Is that clear so far? Okay, but this was only for one subject. So we have to do it for all 100 subjects. That was supposed to be your exercise, but for the sake of time, I do really recommend trying it on your own though, because I have learned most of my things through mistakes. So I hope you do the same. Okay, so I'm showing you solutions. So basically, your job was to write this function in Python. So you basically iterate through the whole every subject, and you basically get this one vector of features per individual. There is usually like the double dipping issue I talked about before. Have I made any mistakes so far by doing this sort of pre-processing? Because this is always the tricky part. Like, is it okay to pre-process? Is it not okay to pre-process? What if I take the PCA? So the main difference basically between what we did right now, taking a PCA type of thing, is PCA happens on the entire group. All the pre-processing we have done so far is on an individual level, right? So it's just, we are basically essentially reshaping the data. We are not really trying to use information from other subjects to influence our data. So far what we have done is completely fine, because we are not actually using another subject's information to influence my information. Okay. So from here, we do splits, the train and test features. And so for your train set, yeah, so for the first task, you're going to use the diagnosis. So I think I showed you the data frame before over here. So we're going to use the diagnostic group column as my label for these features, for these samples. And basically, that's going to be my Y output. So far, so good. And like I said, these are binary outcomes, so we need to encode them as binary labels. So that's what this label encoder is doing, to make them binary. And I'm just printing basically 50 versus how many classes I have of autism versus non-autism. So finally, we have a matrix or the setup like what we want to have. We have one vector per subject, and we have one number as our label. And from here, things should be easy, right? So this is what it does in terms of split. So it's going to be 80 and 20 as my test set split. The stratification, like we talked about this before, we want to maintain the same distribution of labels in our train and test. So here we want to have same distribution of autism and non-healthy controls in our train and test. So that's what my stratification is based on my labels itself. That's what it's saying here. And again, I'm only doing one split here. I'm not doing the entire cross-validation because it will take time. So I'm only doing one split here. So my training has 80 and testing has 20. And feel free to run the model on your laptop. And if anybody has done that, I would be curious to know your accuracy for this. Sorry? For train or test? What about train?
0.82%.
Okay, and what does that tell you then? Exactly. So we got a train accuracy of 82%. I think I have similar numbers here as well. Yeah. So your train accuracy is 82%, but that's not the right one. So we shouldn't get excited with this. When you do on the test set, we get 0.55. So what does that mean? Are we able to predict autism from functional MRI scans? what would be my null performance here? What would be my null performance here? Like if I just had to guess randomly. Sorry. Yeah, because our split is now exactly 50-50, so it's 50%. If it was 75-25, it would have been 75%, because it's easy to just predict the majority of the classes. But in here, it happens to be just 50-50, so it's 50%. That makes sense? Okay. So we are marginally doing better than this. There are papers who have published this, so I would not recommend. But are we only interested into accuracy? This is so tricky to go back and forth. Okay, hopefully this makes sense. So we talked about true positive, false positives, all that stuff. So confusion matrix is the concise way of representing that. So I had 20 samples in my test set. So this is a confusion matrix only on the 20 samples. What does it represent here? Sorry?
Test value is false. It's predicting that it's false and also that it is false.
Right. So it's my. Sorry?
True negative.
True negatives, actually. Because it depends what you call. If you think autism is positive, yes, then it's true negative. But yeah, so I'm predicting basically 3 true positives, basically. When somebody has autism, I'm predicting autism is just 3 people, which is terrible. So does that make sense in terms of how we look at the results? Okay. Now that you know this, I'll let you do the scanning side. If you want to look at the solution, you can look at the solutions. Or if you want to do it yourself, you can do it yourself. And just tell me the results. Yeah, I'll be around. And because I think food is here, so I guess you always want to eat. But it's a similar process. It's exactly the same process. You just change the column of your labels. Just let me know whenever you get a chance what accuracy you see for your site classification. I think I'll stop here unless somebody has questions. No? All good? Cool. All right. Thank you so much. So I was bad before.
Good. You're getting better.
No, but actually, this was much. I mean, going back and forth with outcasts is much harder. Like, in my back of my head, I'm like, I don't know if half the people are here. Yeah, so I should have brought my.
And we should definitely. I mean, the first half hour was see because of the but we could like next time I really have to remember to take those 10 minutes to establish before, because otherwise then they mend their stuff while the thing is going on. And,
I wanted to do that. We just had half an hour. I knew I was going to finish. Usually, if I would be yes, I exactly at 9, I would have spent like half an hour.